This video is on the objective determine the p-value for a hypothesis test for a proportion, right? A population proportion. And this is number 1, so the first video on a question from your homework related to this objective. Let's take a look at it. So as I say almost every video, if you're unfamiliar with the topic, want to see some more about it, what they're doing, click on More Instruction and look at their videos, their notes, their examples, and hopefully those help you out. So here, a software developer claims the proportion of companies that use JavaScript as their primary software technology is different than 61%. To test this claim, a random sample of 720 companies is taken, and it is determined 460 of them use JavaScript as their primary software technology. Now they've set up the hypotheses. I'll go over these again myself. And then they're asking us to find the p-value for this hypothesis test for a proportion and round your final answer to 3 decimal places. We can also use we can either use this standard normal curve here, or I'll use the calculator as well. All right, and show you both. All right, so I'm gonna go to a piece of paper and start writing out some information. All right, start going through the steps of a hypothesis test. All right, let me get rid of the calculator for a second. So the first thing that you're going to do when performing a hypothesis test is to identify a claim. Right, some claim or belief that's being tested. Now the claim here is given to us, the proportion of companies that use JavaScript as their primary software technology. I'll call that P, right, for proportion. So P represents this proportion of all companies that use JavaScript, right, as their primary technology. Now the claim is that this proportion is different, right, is not equal to 61%. Right, so P is not equal to 0.61. Right, once a claim or a belief that is to be tested is identified, then we form our hypotheses. Right? We have a null hypothesis, an alternative hypothesis. This claim does not involve equals, right? It is not equal. So that's going to be the alternative hypothesis. And then, the null hypothesis and alternative hypothesis, they should be opposing statements. So the opposite of not equal to is equal to. All right, and don't forget, this equality here, that P equals 61% or 0.61, that is going to be assumed. Right, you assume that this is true. And then we're going to decide whether or not we like that assumption later, right? Whether or not we're going to reject it. All right. Now there's no alpha mentioned, right? Remember, but usually after the hypotheses we identify a significance level for the test. And since there's no value of alpha mentioned, you can safely assume 5% for now. Unless they specify in a later part of the question. So if alpha isn't mentioned, you can assume 5% pretty reasonably for most tests. Okay, then a sample is taken. Now this sample had a size of 720, right? They took a random sample of 720 companies. And lowercase x here represents the number of successes, and in this particular problem, a success is if they use JavaScript as their primary software technology. So of these 720 companies, 460 of them use JavaScript primarily. And then you have a sample proportion, right? P prime or P hat. You might see either one. They both mean the same thing. All right. The sample proportion of companies that use JavaScript primarily is 460 out of 720, which I'll approximate maybe to 4 decimal places. Why not? All right. I might even just keep the number the way it is. So we got here, pulling the calculator up, 460 divided by 720 is 0.63, 888888888. If I do 3 decimal places, so that's approximately 0.639. Right, so almost 64% of this sample, uses JavaScript as their primary technology. Okay, then remembering that the distribution of p hats, or p primes, remember that the distribution of sample proportions is approximately normal, with a mean of p and a standard deviation of square root of p times 1 minus p over n, where p is assumed to be 0.61. So using that fact, right, the fact that we're working with a normal distribution, we then find the test statistic. Right, the test statistic for our sample proportion here, which is going to be what's the z-score, right, for these tests about a single proportion. It's a z-score. And that z-score is, you take your sample proportion, p hat or p prime. How far away is that from the assumed population proportion here? How far away is that from p? And then how many standard deviations is that, right? That's what a z-score was, right? A number of standard deviations away from the mean. And the standard deviation for the sampling distribution of the proportions was this, right? The square root of p times q, or 1 minus p divided by n. Right. So I'm going to plug in, I'll just use the number I just had. So we got 0.639 minus, and then the assumed population proportion is, the p is 0.61. And this is being divided by the standard deviation of the sampling distribution for the proportions. The square root of, p, 0.61, times 1 minus p, so 0.39, divided by the sample size here is 720. All right. So on my calculator, I'm just going to use the current number I have as my p hat, 0.6388888, like that, and then subtract 0.61. All right, so there's the numerator of this, and then divide by that standard deviation, the square root of 0.61 times 0.39 divided by 720, and making sure all those numbers are underneath the square root symbol. So I get a z-score. If I round it to 2 decimal places, so then I can use that table, I get a z-score, a test statistic of approximately 1.59. Alright. And then I'll draw a picture of a standard normal z distribution with that bell-shaped symmetrical curve. So z-score is on the horizontal axis. A nice bell-shaped symmetrical distribution curve above it. The z-score underneath the peak is a z-score of 0. And then our test statistic, our z-score, right, the z-score for our sample proportion, came in at 1.59. So over here somewhere, right, there's 1.59. This is our test statistic. Now what we're asked for right, is the p-value. What's the p-value of this test statistic? Now, we have to know what kind of a test it is, and I should have mentioned this earlier, but let's go back and look at the alternative hypothesis. All right, the alternative hypothesis is that a parameter is not equal to some value. So what we have here is a two-tailed test, meaning that to find the p-value, I can do one of two things. To find the p-value for this test statistic, I notice that it's on the right side of the center. So what I could do for the p-value is take the area to the right and then double it, right? Because it's got to be two-tailed. So I could do that, take the area to the right of this and then double it, or look at the area to the right of positive 1.59, right, our test statistic, and then using the symmetry, also look at the area to the left of negative 1.59, right, and then both those areas together will be the p-value. So I'll call this maybe area 1 over here, or left area, and this area over here, area 2, right? And then the p-value of our test statistic is area 1 plus area 2, and they should be the same due to the symmetry of the normal distribution. Or I could, like I said, I could have said it was 2 times area 2, right? This area to the right of my test statistic doubled. All right, so I'm going to do that with the calculator. So remember how to find the area under a normal curve on the calculator. You go second, distributions, and then this normal CDF. So what I want to do is find this area to the right of my test statistic, right, the right tail here. So the lower value is my test statistic, 1.59. There is no upper value, so I'm just going to put in some large positive number like 5 nines there. Mean 0, standard deviation 1, because it's the standard normal, right, the z distribution. And this area, right, this area is approximately 0.056, and that means this area is also about that. And then we put them together, or just double this area, right, times 2 gives me the p-value. All right, so putting those together, we get approximately 0.112. If they asked me to round to 3 decimal places. So here's the p-value. All right, there, 0.112, coming from the calculator. All right. Now, if I want to use the table they gave me, just remember that the z-score is 1.59. All right. So if I want to use this table, now remember, the table, a typical standard normal curve table, gives you areas to the left. So if I go to a z-score of 1.59, see how that gives me 94.4% to the left of 1.59? So the area to the right would be 1 minus this, 0.056, which is exactly what I got with my calculator. The area to this area here is 0.056, which is, from that table, 1 minus 0.944. You'd have to do 1 minus the value from the table, because the value from the table gives you the area to the left. And then double this for the p-value. So either way, you look at the table or you use the calculator, round to 3 decimal places, the area of both of these tails, right, for a two-tailed test, the p-value for our test statistic is 0.112. So that's all they're asking for here, so 0.112. And then you would use this p-value and compare it to alpha. All right, whatever alpha is, I assumed it was 5%, and the p-value is 11.2%. That's greater than alpha. And if the p-value is greater than alpha, you reject the null hypothesis. If the p-value is less than or equal to alpha, you don't reject the null hypothesis. And then you make a conclusion, do you have enough evidence to support the claim or not based on that? But all we're asked for here is a p-value. Okay, wonderful. And again, they show you how, hey, they calculated the test statistic, right, approximately 1.59, looked up this value on the table and said, oh, the area to the left of 1.59 is 0.944, so the area to the right's got to be 0.056, and then you double that because it's a two-tailed test. All right, so again, please read through your answer explanations. Okay, so hopefully watching me go through this one, looking at more instruction, all help you out when you're working on this kind of a problem on your own. And thank you for watching.